In this video, we will discuss dynamic equilibrium and Le Chatelier's principle. These are your learning targets. Now, throughout the year, we've talked about many different types of reactions. Synthesis reaction, decomposition, single replacement, double replacement, combustion, oxidation reduction. We just finished talking about neutralization reactions. And typically, when you think about a reaction, you're thinking about reactants forming product. Well, most of these chemical reactions are actually reversible. So when I say reversible reaction, I'm talking about reactions that can go in either direction. It can go from reactant to product, reactant forming product, or product going back to reactant. And you know that this is a reversible reaction because when you're looking at a chemical equation, you're going to see a double arrow. And a double arrow might look like this, or it might look like two half arrows, one pointing to the right and one pointing to the left. If it's pointing to the right, this is your typical normal reactions. We say that the reaction is going forward, that reactant is forming product. Now, when the arrow is pointing backwards, we're talking about a backward reaction where product goes back to reactant, okay? So this is constant. So a reversible reaction means that it can go in either direction. Now, I'm not saying all chemical reactions are reversible, but most of them are. And reversible reactions tend to reach a state of equilibrium in a closed system. So what's a closed system? It's like this picture on the top right of the screen. Okay? A closed system means that there's no exchange of matter, there's only exchange of energy. And it occurs with chemical reactions, and it can occur with phase changes, right? For example, if you're boiling water, and the top is on the pot of water, that is a closed system. So as you boil the water, it's going from liquid to gas, it's evaporating, but at the same time, it's going back from gas to liquid, so that's condensation. So that is also reaching dynamic equilibrium. Okay, so a reaction is at dynamic equilibrium when the rate at which reactants, our reactant to form product, becomes exactly equal to the rate at which products are converting back to reactants. So remember what rate is. Rate is speed. So we can think of it as the speed of the forward reaction is equal to the speed of the backward reaction. So again, forward reaction meaning reactant to product, and backward reaction meaning product to reactant. This is where the speed is constant, okay? Speed is equal. So if you're having a hard time trying to understand what that means, think about running up an escalator that's going down. Now, how many of you have actually tried to do this? I bet most of you who are listening to this video, right? So imagine an escalator that's going down and you're trying to run up the escalator. Okay, so if you want to get back to the top floor, you have to run as fast as you can. But what if you want to stay at the middle of the escalator? You have to be going up the same speed as the escalator is going down, right? That right there is dynamic equilibrium. So I'm going to show you this video just to give you another visual of dynamic equilibrium.
Imagine you are digging a hole. You got it? Imagine, as you are digging that hole, your friend is refilling it. If you are digging the hole faster than your friend, the hole gets larger. If your friend is filling the hole faster than you, the hole gets smaller. But if the two of you are working at the same speed, there would be no change to the size of the hole. The same concept can be applied to a reversible reaction. If the rate of the forward reaction, reactants to products, is the same as the reverse reaction, products to reactants, the reaction is said to be at equilibrium. This is called a dynamic equilibrium because both processes are occurring simultaneously, even though there is no overall observable change.
Now, even though there's no observable change, I don't want you to think that the reaction stops or that things are complete. At a molecular level, things are still moving. If I take you back to the escalator example, and I'm asking you, what do you need to do in order to stay in the middle of the escalator? Well, think about it. You're constantly moving, right? What happens if you just stop once you reach the middle of the escalator? Well, the escalator is going to take you down, okay? But in order to stay in the middle of the escalator, you are constantly moving your feet, you're probably moving your arms. The point is you are constantly moving as the escalator is also moving, okay? So that is what's happening at the molecular level as well. Things don't stop, but things are constantly moving as the speed of the forward reaction is equal to speed of the backwards reaction. Sometimes a stress might be applied to a system. A system is a reaction at equilibrium. And so what is a stress? A stress is any kind of change in a reaction at equilibrium that will upset that equilibrium. So what are some examples of stress? Increasing the concentration or decreasing the concentration. So adding more of something or taking away something. Heating something up or cooling it down, so increasing the temperature or decreasing the temperature, or a change in pressure, okay, increasing pressure or decreasing pressure. So just like when you get stressed, you want to do whatever you can to get rid of that stress, right? And so according to Chatellier's principle states that if a stress is applied to a system at equilibrium, to a reaction at equilibrium, the reaction proceeds in the direction that relieves the stress. So this reaction will also do whatever it can to relieve the stress. So we use Le Chatelier's principle to predict how changes in concentration, temperature, and pressure will affect equilibrium. Let's first take a look at concentration. Increasing the concentration of reactants in a reaction at equilibrium results in the reaction shifting right meaning moving the reaction forward, and proceeds towards the products, which results in the formation of more product molecules. So think about it a little bit. If we are now adding more reactants to the reactant side, think of it as the reactant side is more stressed, and so the reaction is going to do whatever it can to relieve that stress. So it's going to push a lot of the reaction towards the opposite side. So it's going to push it to the right, meaning pushing it forward, reactant to product. Increasing the concentration of products in a reaction at equilibrium results in the reaction shifting left, meaning it goes backwards. So product to reactant proceeds towards the reactants, which results in the formation of more reactant molecules. So I'm going to use this as an example. This is cobalt 2 hydroxide, and we're going to add hydrochloric acid to it. And it forms cobalt 2 chloride and water. So as you can see, this is a reversible reaction. At equilibrium, this reaction is a purple color, okay? And if we have more of the reactants, then the color will turn pink, like you see here on the right. And if it has more of the product, then it'll turn blue or really dark purple, which is on the left side of this picture here. So if we put stress on the reactant side, then the reaction will shift, the equilibrium will shift to the right, and it'll move forward towards the product. If we put stress on the product side, then the reaction or the equilibrium will shift left, and it'll go backwards towards the reactants. So, for example, I'm going to show you a video where someone is demonstrating this reaction. So if we add more hydrochloric acid, we are adding more reactants, right? We are increasing the concentration of hydrochloric acid. Well, there's lots of stress on the reactant side, so Le Chatelier's principle says, in order to relieve that stress, all of this, kind of think of it as there's too much on this side, so it shifts the equilibrium to the right, and it'll go that way to create more product. So let's take a look at this video to see if our prediction is true.
And watch what happens. You see the solution goes blue. If I stir it round, it's not fully blue, but it's gone a darker purple, a bluer purple. And if I keep adding hydrochloric acid. You can see a very intense blue colour there. Eventually we will get to a complete blue.
So as you can see, our prediction was right. If we add more hydrochloric acid, it'll shift the equilibrium to the right. It'll shift the reaction to the right to create more product, and that's why it turned blue. So now let's take a look at this. If we were to add more water, which is a product, which way will equilibrium shift? So think of it as there's too much product, right, on this side. So Le Chatelier is saying it's going to do the opposite. So now that we have too much product, it will push everything to the left, and we are going to find that as the reaction goes backwards, we are going to create more reactant, so it will turn pink. So let's see if our prediction is correct.
The amount of water in our system, just pour in some water, and straight away you could see pink, and didn't take much water. We've already gone back towards the sort of purple colour we started off with, and
so as you can see, what we predicted was correct. Let's take a look at this example. So here is our reversible reaction at equilibrium. If we increase the concentration of carbon monoxide, which way will the reaction shift? So think about it. There's too much reactants. Okay, so too much reactant, it's going to push it to the other side, right? It's going to push away, so it's going to make the reaction shift right. What if we take away water? Okay, so think of it as which side has more, or which side is heavier, because the equilibrium will shift away from the heavy side. So now if we take water away, technically this side is lighter, right? We took something away, the equilibrium will shift so that we are creating more product, okay? So here, in this case, here's the heavier side, here's the lighter side, so then equilibrium will shift to the right. Now let's take a look at changes in temperature. The first thing that we need to go over is the difference between endothermic and exothermic. So remember the difference between those two? Endo means heat absorbed. Heat is part of the reactants, where exothermic is heat released, and heat or energy is part of the product. And so when you look at it in a reaction, for example, it's going to look something like this. Heat plus A plus B yields C plus D, right? So heat is part of the reactants. Heat, this can be energy. It could also be a numerical value, like delta H. It might say delta H is positive. Those are all hints that it's an endothermic reaction, okay? And so exothermic, heat would be part of the product. It might say energy on the product side, or they might say that delta H is equal to negative. Okay, so again, all hints that's telling you that it's exothermic. So if you add heat to an endothermic reaction, the reaction shifts to the right. And so you're going to treat heat as if it is a substance. Okay, so in this case, I'm going to treat heat like it is a reactant. All right, and so if I increase the heat, think of it again as it's too much on the left side, on the reactant side. So according to Le Chatelier, it's going to push everything to the right. Okay, it's going to push the reaction to the right to create more product. Okay, so when I show you this arrow up here, I'm just indicating that it's going right or to the left. Okay, equilibrium is going to the right, or equilibrium is going to the left. If you add heat to an exothermic reaction, so now notice that heat is part of the product. If you add more heat, so then the product is too heavy, right? That's a way to think of it. Then the reaction shifts to the left, okay, to relieve that stress. Now, what if we were to take away the heat, meaning we were to cool it down? So for an endothermic reaction, if we take away the heat, Remember, this is the missing piece, okay? Le Chatelier says it's going to do whatever it can to basically fill up that void, okay? Fill up that hole. And so for this, equilibrium will shift left. For exothermic reaction, if we take away heat, then it's on the product side, right? So that means the reaction will shift to the right towards the product when we cool something down, okay? So again, treat heat like it's a substance. Either it's going to be a reactant or a product, and just like we did with concentration, you're just going to think of it the same way. Now, for temperature, it's important that you know the difference between endothermic and exothermic, because that will determine the equilibrium shift. So we're going to take a look at this example again, and you'll notice that I added heat to this reaction, and heat is on the reactant side, which tells us that this is an endothermic reaction. If we increase the heat, then what do you predict is going to happen to the equilibrium shift? It will shift to the right towards the product, and you would predict what color, or we'll see what color. A bluish color, okay? What if we decrease the heat, meaning we cooled it down? Then the reaction will shift to the left towards the reactants, and we will expect a pink color. So let's see if our prediction is correct.
Purple solutions, and I'm going to put one of my solutions in ice. So in it goes. I'm going to leave one of my solutions at room temperature, and in my third solution is going to go in water that I boiled a couple of minutes ago from the kettle. Let's see if we can spot any difference.
So after about a minute, this is what we're going to see.
Now, and if I take them out, okay, the difference between the one on the left and the middle isn't that great, but the one on the right you can see has gone very blue.
And what we predicted was correct. If we increase the heat, the equilibrium will shift to the right, and we'll get a blue color, which happened up here in the test tube. And then if we cool it down and we put it in ice, then equilibrium will shift to the left, and we will get a pink color. The last stress we're going to talk about is pressure. And remember that pressure has to do with gas molecules. When gas molecules collide with each other in the walls of the container, it creates pressure. So if you increase the pressure in a gas reaction, the reaction shifts towards the side with fewer moles of molecules. So take a look at this example. Nitrogen and hydrogen produce ammonia. These are all gas molecules. And how do you determine the number of moles? Well, remember, you're just looking at the coefficients. So here we have 1 mole of nitrogen and 3 moles of hydrogen to give us a total of 4 moles of reactants. Whereas on the product side, in this case it's just ammonia, we only have 2 moles. So if you increase the pressure for this reaction, the reaction shifts towards the side with fewer moles of molecules. So which way will the reaction shift for this example? If you said it shifts right, you're absolutely correct. It's going to shift towards the side with the fewer moles, which in this case is 2 moles. So if you decrease the pressure in a gas reaction, the reaction shifts towards the side with more moles of molecules. So again, looking at this example, which way would the reaction shift? It would shift left, towards the side with the more moles of molecules. Now, if there's the same number of molecules on both sides, so if it was, for example, 4 moles of reactants and 4 moles of product, well, if you increase or decrease the pressure, it has no effect on the reaction. And keep in mind that this only applies to gases. And what happens if you add a catalyst? Well, nothing. Remember, a catalyst simply speeds up the reaction. It will have no effect on the equilibrium shift. Now let's take a look at an example. We're going to look at the reversible reaction, nitrogen and hydrogen forming ammonia. This is an exothermic reaction, and I know that because heat is part of the product. And we're going to predict which way the reaction will shift when we put a stress onto this reaction. And then we're going to predict what will happen to the concentration of each of these substances. So again, these brackets mean concentration. It means molarity. So will the concentration of each of these substances increase or decrease as the reaction shifts to the right or to the left? So the first stress that we have on our sheet is adding nitrogen. So when we add nitrogen, we're adding more of this, and it'll shift the reaction to the right, so it points towards the product, and all of the products will increase while the reactants will decrease. Now nitrogen has a line through it because that's the one that I'm changing, okay? And so I'm not going to put anything there. Another way to look at this is if the reaction is shifting to the right, I'm going to draw an arrow that points to the right. And wherever the arrow is pointing, those substances will increase, while at the tail of the arrow it's going to decrease. So if we add hydrogen, so remember this side is heavy now because hydrogen is a reactant, so overall the reactants are pretty heavy. Which way will the equilibrium shift? It'll shift to the right. Okay, so imagine that there's an arrow pointing to the right. So that means that all of my reactants will decrease, okay, while ammonia increases because we're making more product. Now, what if we add ammonia? So if we add more product, so again, this is the heavier side, right? So if we add more product, which way will the reaction shift? It'll shift left. And so imagine that there's an arrow pointing to the left towards the reactants. That means all the reactants increases while the products would decrease. Now, what if I take nitrogen away? So remember, think of it as there's a hole there. I just made a hole and I want to fill it back up. Okay? So if I take nitrogen away, that means the reaction will shift left towards where that hole is. Okay? So it'll shift left. That means the reactants will increase and my product will decrease. What if I take away hydrogen? Again, hydrogen is on the reactant side, right? So which way will the reaction shift? It'll shift left. And again, reactants will increase while product decreases. What if I take away ammonia? Ammonia is a product, right? So the reaction will shift to the right. And both of my reactants will decrease. Now, what if I increase the temperature? If I make it hot? So heat is on the right, it's on the product side, it's exothermic, so it's on the product side. If I increase the temperature, remember, just treat this as if it's a product, then what will happen to the equilibrium? It'll shift left. And both reactants will increase while my product decreases. If I cool it down, then again, I'm taking away heat, and that's the hole, right? And so equilibrium will shift to the right, and my reactants will decrease and product will increase. So now what about pressure? Remember, what do we have to do with pressure? We have to count up the total number of moles of reactants and the total number of moles of product. So here we have 1 mole plus 3 moles. That's a total of 4 moles of reactant. And on the product side, we have 2 moles of product. Now, even though heat is written here, we don't count that as a mole, right? So we have 2 moles and 4 moles. So if we increase the pressure, which way will the reaction shift to? It'll shift towards the smaller number of moles, so it'll shift right. And then both the reactants will decrease while product increases. If you decrease the pressure, equilibrium will shift towards the higher number of moles. So in this case, it'll shift left, and then both reactants will increase while product decreases. Let's take a look at the next example. We have an endothermic reaction here. Energy is part of the reactants. H2 plus I2 make 2HI. Go ahead and pause the video and try these problems out yourself. It's similar to what we just did, I just didn't give it to you in table form. Explain what happens to the reaction when HI is removed. Well, when HI is removed, the reaction shifts to the right, towards the product, and the concentration of the reactants will decrease. Explain what happens to the reaction when H2 is added. When H2 is added, the reaction shifts to the right, and there will be a decrease in concentration of the reactants. And what happens to the reaction when the reaction is cooled down? Well, the reaction will shift to the left, towards the reactants. There will be an increase in concentration of the reactants and a decrease in concentration of the product. Explain what happens to the reaction when increasing pressure. So did you remember to count up the total number of moles? If you did, great. Remember, energy is not a mole. Okay, so here we have 1 mole plus 1 mole, that's a total of 2 moles. On the product side, we have 2 moles of product. So 2 moles of reactants and 2 moles of product. What's going to happen to the equilibrium? Nothing. It's the same number of moles on both the reactants and product side. And that's it for equilibrium and Le Chatelier's principle.